So yes, JEE and NEET exams are very near, and we need to do a quick revision of the chapters like S block, P block. Yes, so come with me and we will do a very quick revision of the S block elements. You cannot waste too much time. You don't have too much time also. You've got to focus on a number of things. So let us go to the S block elements. So first of all, the S block elements. What are the S block elements? Yes, you definitely know it. I know that you know it. So, but we will list down the elements: lithium, sodium, potassium, rubidium, cesium, and francium. So if you are looking for a mnemonic to remember it, so this is ली ना के रब से फरियाद. कुछ भी फरियाद कर सकते हैं कि यार चलो जेई नीट पास करा दो यार. Okay, तो लीना के रब से फरियाद for lithium, sodium, potassium, rubidium, cesium, and francium. Going on, yes, going on to the challenges. We are speaking about the atomic radii. Going on to the atomic radii, you know that, see, I have listed down in Armstrong the atomic radii for you all to, yes, know it. So lithium, 1.23 Armstrong, 1.57, 2.03, 2.16, 2.35. So francium, we will not talk about it because it's radioactive. Yes, and if you see the trend that the atomic radius increases down the group because of the increase in the number of shells. So, you must be thinking beryllium also, yes, together. So, group 1 elements I've listed down. Group 2 elements are beryllium, magnesium, calcium, strontium, barium, and radium. So, the mnemonic that you may be looking for is, this is my Baymug. Baymug is the name of the person. You can say Ka, Sir, 12 सर है. रावण का 10 सर है, लेकिन मेरा बेमग का 12 सर है. So बेमग का सर 12. These finishes the group 2 elements, and yes, to the discussion of the radii. Once again, if you see beryllium, magnesium, calcium, strontium, barium, radium, once again it's radioactive, so we have not listed it down. So once again, the atomic radius increases down the group. I have listed it across, so it takes less space for me, but this entire description is about down the group. Atomic volume. If you look at the atomic volume of lithium, beryllium, lithium, sodium, potassium, rubidium, cesium, again increases. What is atomic volume? Density is mass by volume, or volume is equals to mass by density. So you can say that the mass and the volume has a direct relation. So mass increases, volume increases. So atomic volume increases down the group. And if you have a look at the data that I have collected for you, the atomic volume increases down the group for group 2 elements also. Going on to the density, same relation which I had quoted, I will quote it once again. Density is mass by volume. So density and mass are directly related. So 54, 97, 86, 1.53, 1.87. So for potassium, we have a slight decrease in density. And this decrease in density is in gram per milliliter. It hardly matters. So, but still, you have to remember this exception, and you remember this exception because I've collected this data and written down for you. Same with beryllium to magnesium, it increases. Beryllium to magnesium, it increases. Then calcium, and then it further increases only. Let's go to the solid state. So if you see, from lithium to sodium to potassium to rubidium to cesium, we have a BCC structure, body-centered cubic lattice. But for group 2 elements, it varies from HCP to FCC. Okay, from HCP to FCC, hexagonal closed pack to face-centered cubic. So this is just a trend that you need to remember. Yes, you need to remember a lot of things, but the atomic radii, the atomic volume, the density need not have any remembrance because it increases down the group. What you need to remember is just the HCP and the FCC for beryllium and so on. Next, going on to the metallic character, it increases down the group because, the size increases. So it would be easy for the elements to lose electrons. And if the elements can lose electrons faster, means the metallic character is high. Same with group 2 elements. The metallic character increases down the group because of similar reason, but here are a few exceptions. So beryllium to magnesium, the metallic character decreases, but it increases from magnesium to calcium, then again it decreases, and then it decreases, and then it decreases. Oh, so why does the metallic character decrease? We can take up some MCQs. Keep this recorded. Keep this, revise it, go through it again and again, and it will definitely settle down in your head. So if you see next about the boiling point decreases. The boiling point decreases, but slightly increases for cesium. So in general, it decreases, but it is slightly higher because of a lot of characters responsible for the boiling point for cesium, which brings it a little higher. Next, for group 2 elements, I have listed down. See, 27701107. So pause the video. From beryllium to magnesium, it decreases, and from magnesium to calcium, it increases. So it is DI, DI, D. Oh, so easy. DI. D means decreases, I means increases. DI. Okay, so it is homogeneous. That's how you remember it. Next, the melting point also, it decreases. Naturally, if the boiling point decreases for alkali metals, the melting point would also decrease for the alkali metals down the group. Again, let us see whether this DI, it goes on here also. Yeah, you need to remember, come on. DI. So for the melting point and boiling point for group 2 elements, the DID concept start with a D. DI happens. Okay, decreases, increases, decreases, increases, decreases. Let's go on to the ionization and energy or ionization enthalpy. So we go on to the ionization energy. Ionization energy, it decreases. It decreases. So ionization energy has been given in electron volt. That means it would require less energy to take out the electrons. So as the metallic size increases, so if the metallic size increases, we know that it is easier to pull out the electrons. Naturally, the ionization has to decrease. So here we have one electron. So we have spoken about first ionization enthalpy only in alkali metals. But in alkaline earth metals, you have 2 electrons to be taken. So I've listed down the first ionization enthalpy. If you see the first ionization enthalpy, it decreases. So the slight 0.1 electron volt increase. So we can say that it decreases from magnesium to radium and barium and then radium. It's nearly same. The second ionization enthalpy also, it would be the same. It would decrease. It is more metallic, so it would be definitely easier to pull out the electron. Okay. So going on to the next characteristic, the electropositivity. They are all metals. So if you go down the group, the electropositivity would increase because it would be easier to lose the electrons. If they lose electrons, they are electropositive, and if they gain electrons, it is electronegative. So they are all becoming more and more metallic when we go down the group. So electropositivity increases, be it for the group 1 series or the group 2. Woo. Now let us go to the reduction potentials, and that we have listed in volts. So if you see the reduction potential, lithium is having the most negative, reduction potential. Then it is 2.71, then 2.93 negative, 2.99, and 2.9. So that means the reduction potential for lithium is the highest, and then it is cesium, which is equal to rubidium, which is greater than potassium, and then it is gold. So this is how it happens for the group 1 elements. Okay, you can have a look at it just once, twice, and I know it will get recorded in your brain. Now going on to the group 2 reduction potential values, it increases. It increases. So you need not worry at all. It increases from beryllium to barium. That means what? Barium has the capacity to reduce something and itself get oxidized. They are metals, they have a tendency to get oxidized. So barium has the maximum tendency among the group 2 elements to reduce something and get oxidized. Going on to the reducing power in solution. So it is in solution, it is lithium which will reduce the most compared to cesium, rubidium, potassium, and sodium. If you can see, there is this equality of cesium and rubidium, it minimizes to greater. So just the record. And if the reduction potential in not a solution increases, then in solution also it will increase. The reducing power in air. When we say reducing power in solution means aqueous solution, and reducing power in air means non-aqueous solution. So cesium has the highest tendency to get reducing power in air is the highest. So cesium, rubidium, potassium, sodium, and lithium. And here also it increases from beryllium to radium. The color imparted to the Bunsen burner for lithium, it is crimson red. For sodium, it is golden yellow. For potassium, it is pale violet. For rubidium, it is violet. And for cesium, it is also violet. That is the color imparted to the Bunsen burner. Here, for beryllium and magnesium, because the electrons do not get excited with the flame energy, they do not show coloration to the flame. But from calcium onwards, the flame coloration it changes to brick red because it is easier for the flame energy to excite the electrons and impart a red color to the flame. Because of the transition of the electrons, the flame color is red. So brick red for calcium, strontium is crimson red, barium is green, and radium is orange. So remember it. Hydration energy. Hydration energy I have listed for lithium is minus 480, sodium is minus 371, potassium is 291. But I have, for rubidium and cesium, the values vary. And so I have not written, there's a lot of variation in the value. So the hydration enthalpy, it increases from lithium to cesium. And from beryllium to barium 2 plus also the hydration energy increase. Okay, that means hydration energy means once you dissolve this iron in aqueous solution, it will get hydrated, surrounded by water. And when it gets surrounded with water, it will release the maximum amount of energy. That is the meaning. So the negative sign is for the release of energy. So hydration enthalpy negative means lithium ion would get hydrated and release the maximum amount of energy. So going to hydrated ionic radii, the hydrated ionic radii would be the highest for lithium because it would get maximum hydrated and then it would decrease in cesium. So same with the group 2 elements, it decreases from beryllium to radium. Reactivity in air, it increases from lithium to cesium. The reactivity increases from lithium to cesium. So if you give it air, it will get oxidized to oxide. If it is again dropped in water, it will form the respective hydroxide. And the hydroxide is dropped in carbon dioxide, it will form the metal carbonate. There is a possibility for sodium to form not only the normal oxide, to form the peroxide also like Na2O. So sodium has a tendency to form peroxide, Na2O2, when reacted with air under different conditions. So sodium can form the normal oxide Na2O and the peroxide Na2O. Potassium, there is a tendency for forming the normal oxide, the peroxide, and also the superoxide. Okay, which has not been listed here, but you can note it down. Lithium, there is a problem with lithium also. It not only combines with the oxygen of the air, it also combines with the nitrogen of the air to form the respective nitride. Okay, so this has been written down for you. Now, if we go to the reactivity, it increases from beryllium to barium. Beryllium does not react with air. Okay, barium in powder state it bursts into a flame on exposure to air. Beryllium, magnesium, and calcium, on heating with air, it combines with the nitrogen of the air also to form the respective oxides, not only the oxides. But you get a mixture of the oxides and the nitrides for beryllium. You get not the oxide but the nitride, magnesium oxide and nitride, calcium oxide and nitride. Okay, so this is it's like a cheat cake. You have a book of Britannica and you have to, learning it before your exam. So we go to hydrides. We have lithium hydride, reactivity decreases. From lithium hydride is most reactive, best hydride donor, lithium hydride, and it decreases till cesium hydride. But for beryllium hydride to barium hydride also, the trend is reversed compared to the alkali metal hydride. The hydrides BaH2 is a better hydride compared to BeH2. Okay, so the trend is written. The ionic character increases, the metallic character increases. Down the group means the ionic character will increase, and the stability of the ionic character will decrease. Going on to the properties. If we take the hydrides and we drop it in water, it will form the respective hydroxide, releasing hydrogen gas. So this reactivity, the reducing power, will increase from lithium hydride to cesium hydride. Going on to beryllium hydride to barium hydride. Beryllium hydride and magnesium hydride do not react with water. But the rest of the elements like calcium hydride, it reacts with water, say it forms calcium hydroxide, releasing hydrogen gas. Why? The reason why beryllium hydride does not react with water is because it exists in the bridged structured state. The bridge structured state has been drawn for you. Going on to the oxides. The oxides, I just told you that calcium has a tendency to form the normal oxide, the peroxide, and the superoxide. So the normal oxide, more oxygen is given to form the peroxide and then the superoxide. The tendency to form the superoxide increases because the superoxide anion is larger in size compared to the normal oxide anion, and so larger the cation, larger the anion, the polarization, the overlap is better, and so the peroxide formation is stable. Going on to the oxides of group 2 metals, you can form the normal oxide and the peroxide only, not the superoxide. Beryllium, if you want to, first of all, I had told that it does not react with oxygen. But it will react with oxygen if the temperature is above 600 degrees Celsius. Okay. But magnesium reacts with oxygen just on burning. So burn it, you know that magnesium reacts with oxygen, giving you a white flash of light, forming magnesium oxide ash. Yes, so this is what is there. But beryllium has a problem. Heat it above 600 degrees Celsius, and then it starts reacting with oxygen. Going on to the next. Oxides. The type of oxides, M2O type of oxide increases, the stability increases, the solubility in water increases. So I've listed it down together. The group 2, the MO type of oxides, the MO type of oxides, the ionic character increases, only beryllium oxide is covalent. Okay, remember beryllium oxide is covalent. The stability increases, the stability of the oxide increases down the group. The solubility also increases down the group. Anytime you feel that I'm going a little too fast and you pause the video and it will, you can absorb it better. If you want, you can take down a pen and a paper and write down a few things like the exceptions. Exceptions happen. So just like beryllium oxide is covalent. So write it down, beryllium oxide is covalent. You write it once and it gets registered. Going on to the basic strength, the lithium oxide is weakly basic. All the others are highly basic because they are becoming more and more metallic. When an oxide becomes more and more metallic, the basic character increases. So that means if you drop these oxide in water, it will form the respective hydroxide. Okay, so I've just written it ionically. You can just check it out here. I like this format, so I've listed it down. Same with, see, I told you exception. So these are all experimental. We cannot help it. I cannot help. So beryllium oxide is amphoteric, whereas magnesium oxide is weakly basic, and the basicity increases down the group because of the increase in metallic character. When the metal oxides of group 2 are also dissolved in water, it forms the respective hydroxide, but here the hydroxide differs. Here you get, say, sodium hydroxide because it is univalent, whereas in case of magnesium and other alkali metals, you get the OH twice. Keep that in mind. Going to the peroxides and the superoxides. The peroxides of the type M2O2, like sodium peroxide, potassium peroxide, lithium does not form the peroxide because of the small size. So the tendency to form peroxide will increase from sodium to cesium. If you take the peroxide, dissolve it in sulfuric acid, you will get the metal sulfate back with hydrogen peroxide. So if you put the peroxide in water, you again get your hydrogen peroxide back along with the metal. Going on to group 2, because the stability only strontium and barium they form the peroxide, and the stability of peroxide increases from strontium to barium. So if you try to do the same kind of reactions with sulfuric acid or with water, it would be the same thing like your alkali metal, peroxides and super. Going to the hydroxide, I've just listed it down, but the ionic character increases, the basic strength also increases. Here for group 2, hydroxide also the ionic character increases and the basic strength increases. But remember that lithium hydroxide is weakly basic due to large covalent characteristics. When an element is small in size, it tends to develop covalent characteristics than ionic characteristics, and a lot of Pajan's rule is being just applied here. Same with beryllium hydroxide, it is amphoteric due to the small size, forms much more covalent. Going on to the halides. So we have lithium halide, sodium halide. So if you take the fluoride, bromide, iodide, the ionic character increases from the fluorides to the iodide. Same with the alkaline earth metal fluorides to iodides, also the ionic character increases. And the solubility in water also increases from fluorides to iodides, which is similar for alkali and both alkaline metals. Last, the carbonate. I hope you really appreciate this small work of mine where I have condensed everything in the form of a flowchart, snapshot. So, yes, this is a quick reading and you have to be quick in these stuff. So, you have ionic character for these compounds increases, the thermal stability increases for the carbonates. Only lithium carbonate is unstable, and if you heat it, it will decompose to lithium oxide and carbon dioxide. So it's not impossible to store lithium carbonate. You can store lithium carbonate in an atmosphere of carbon dioxide, where you will prevent the bad reaction from happening. The decomposition will not happen if you put it in the atmosphere of carbon. And same with all these group 2 carbonates, the ionic character increases and the thermal stability also increases, and they all decompose to the oxide and carbon. Okay. So going on to the important compounds of alkali metals, it's sodium carbonate, Na2CO3 dot 10H2A, which can be prepared by the Solvay process. Also, it's called the sodium ammonia process. The raw materials which are required are sodium chloride, ammonia, and limestone, which is CaCO3. So in the first step, ammonia reacts with water in presence of carbon dioxide to form ammonium carbonate. This ammonium carbonate is further reacted with water in presence of carbon dioxide to form ammonium hydrogen carbonate or ammonium bicarbonate. In the third step, the ammonium hydrogen carbonate is reacted with sodium chloride. Obviously, we're preparing a sodium compound, so we need some sodium source. And the best source of sodium is sodium chloride. And sodium hydrogen carbonate is decomposed when heated to sodium carbonate. In the last step, you see, you get sodium carbonate, water, and carbon dioxide. The sodium carbonate can be combined with 10 molecules of water to give your sodium carbonate or washing soda, which is Na2CO3 dot 10H2O. So just a small question which may be asked in this. So what happens is you can prepare sodium hydrogen carbonate by this process, but if you want to prepare potassium carbonate by this process, Solvay's process cannot be employed because potassium hydrogen carbonate is fairly soluble in water. We require a PPT, a precipitate. A precipitate should be filtered, heated, and then it can give you sodium carbonate. So that's the problem with preparation of potassium carbonate by Solvay's process. Going on to the next compound, crude sodium chloride, it need not be prepared. It is obtained from seawater, and seawater is a good source of sodium chloride, and it's obtained by the crystallization of brine. And this contains sodium sulfate, calcium sulfate, and impurities like magnesium chloride and calcium chloride, which are deliquescent. Deliquescent means it absorbs moisture easily from the atmosphere, and that is why you see sodium chloride getting soggy. It appears very soggy, not because of sodium chloride, but because of the deliquescent substances, magnesium chloride and calcium chloride present in them. Going on to the next important compound of sodium, which is sodium hydroxide, which is commercially prepared by the electrolysis of brine, sodium chloride, using a Kastner-Kellner cell, using a mercury cathode and a carbon anode. So the cathode, the sodium picks up the sodium ion picks up the electron. Of course, it is amalgamated, otherwise sodium is very reactive. So it will give you sodium amalgam. Sodium amalgam means sodium is mixed with mercury. So you get sodium amalgam, and then at the anode, the Cl minus gets converted to chlorine gas, liberating electrons. The sodium amalgam is dropped in water to give you sodium chloride. Mercury comes out, it can be reused, and hydrogen is evolved in the process. So that finishes the important compounds of sodium. We'll go to some important compounds of calcium, which is quicklime, CaO. And how is it commercially prepared? By the decomposition of calcium carbonate, which you have known from a very young age. So calcium carbonate, when heated, gives you calcium oxide and carbon dioxide. So if quicklime is added to water, what is obtained is slaked lime, which is calcium hydroxide. Now, a suspension of slaked lime in water is called milk of lime, while if you have a filtered solution, that is called lime water. So be a little careful about the milk of lime and lime water. The clear-cut difference is given. Quicklime is used for making caustic soda, bleaching powder, calcium carbide, mortar, cement. These are the various uses which you have, and why that is why quicklime is a very important commercial compound. Going on to gypsum, which is calcium carbonate .2H2, which you have got in your 10th standard also, but you may have forgotten. So just a little reminder that when gypsum is heated at 393 Kelvin, it loses 3/4 of its water crystallization and forms a hemihydrate, which is calcium sulfate .half H2O, known as POP, or plaster of Paris. And if you take 2 moles of plaster of Paris, 2 moles of gypsum, and you burn it, you get CaSO4.2H2O, 2 moles of it, plus 3H2O. It becomes, anhydrous. So that's anhydrous calcium sulfate is called dead burnt plaster. Okay. Once again, let us go through the previous reaction. You take calcium carbonate, calcium sulfate .2H2O, and 2 moles of it. You can dehydrate it to 2CaSO4.H2O plus 3H2O. But if you want complete dehydration of calcium sulfate, you have to heat it above 393 Kelvin. That will give you only calcium sulfate, which is called dead burn plaster. Now you know that plaster of Paris has the property of setting into a hard mass when it is mixed with powder and it is set aside. So that is how the casts are prepared. Okay, the casts are prepared. So slight expansion occurs during the setting as water is observed. So CaSO4.2H2O is formed. Now, going on to cement, which is also an important compound of group 2 elements. And the cement, you have noticed, it is a dirty grayish heavy powder. It contains what? Calcium silicates, aluminum silicates, and it's used as a building material. Yes. So cement consists of trisilicate, CaO.SiO2, 3 moles of it, dicalcium silicate, which is 2CaO.SiO2, tricalcium aluminate, calcium aluminate, which is CaO with Al2O3, and tetracalcium aluminoferrate, right? 4CaO.Al2O3.Fe2O3. Yes, you have to learn it for the time being. I never know the type of questions which will be asked. So the average composition of cement, Portland cement, if you are speaking of, it contains calcium oxide 50 to 60%, silicon oxide 20 to 25%, Al2O3 5 to 10%, magnesium oxide 2 to 3%, Fe2O3 1 to 2%, and the rest is sulfur trioxide, which is 1 to 2%. Once again, we can repeat this, that cement sets into a hard mass when mixed with water, and gypsum is added to slow down the process of setting so that it gets sufficiently hardened. Otherwise, what happens? It's brittle. So that's why, it should it should harden very slowly. Going on to the biological importance of calcium and magnesium. If you're interested, just read it. And the rest of it, yes, we have MCQs once again. These are the MCQs which are there. No, I will not discuss the answers right now. It would be aired in the next episode. These are the MCQs which we have for you. How many MCQs, you must be wondering? Not much. There would be just 24 MCQs which I've listed down for you. You could solve out the MCQs. It's not that all the answers to these questions will be obtained in the PDF itself. In the video itself, you have to do a little bit of hard work in order to succeed. So yes, do keep your answers ready if you're interested. And when the next episode is aired, you will get the answers to all these questions. So happy watching, and do not forget to like and subscribe. Thank you so much for watching.